So it starts at the announced time.
Yes.
Yeah, sure.
Yeah. Okay, so maybe I'll start. And so now we will take, so X will be an Okounkov variety, and this have been very much a presence at this conference. This is a symplectic resolution, but what will be important is not that this is symplectic resolution. What will be very important is that X is the stable and also semi-stable locus in some stack. Where, well, the stack is of the form, you take mu inverse of 0 and you divide by G. And so in particular, it's something, well, it is symplectic, but it's also something of the form an LCI affine variety divided by reductive group. And these are the, what?
Just LCI, yes.
What?
It's not just LCI, it's just CI. Just complete intersection.
Yeah, okay, okay. I mean, in particular, LCI. I don't think, I've never seen abbreviation CI. I think it will really confuse people. If, and so,
CI defined as CIA.
so in this situation, one can define a certain curve counting theory, namely, one defines a space of quasi-maps from some pointed base curve V. And this can be, the curve can be, maybe it's nodal. I'll draw a smooth curve. And it's pointed, I need points of different colors. So I'll try to sweep all technical details under the rug, but some of them will just, so that not to lose. That blue, there was blue somewhere. Right, blue. So there'll be some maybe blue points. Can you tell the blue points from the white points?
Size for sure.
Yeah. And so this is how we consider maps to X. So this, and the reference for this, well, there's a long story of the study of this quasi-maps, but the reference, the best modern reference is the paper by Davesh and Jonats and Bumsik. So I'll write it like this. Bumsik, Chapman, and Malik.
Maybe K. Bumsik's his first name.
Oh yeah, right. That's right. Yeah. Okay. Right. So so this space is defined as, so you look at, these are maps to the stack, really. So what's a map to the stack? Is a G bundle over your curve together with a section of associated X of associated pre-quotients, such that evaluate that take value that evaluate to X away from finitely many singular points. Away from, maybe from finitely many single points, maybe I'll draw them in red. And so maybe I'll draw a nodal curve. So this crosses, they have to be away from the nodes and have to be away from the, they can sit on top of a white point, but they have to be away from the blue point.
Away from?
From the blue point. So away from finitely many crosses, where the set of crosses, this is disjoint. The set of these crosses disjoint from the set of blue points and nodes. This is stability condition, and this is the to have a proper moduli space like this, you need this both the pre-quotient be affine and the group to be reductive. Otherwise, very simple. If you go away from this description, it's very easy to see. So in general, maybe I'll say one word in general. So if we're all familiar with coffee and cake, and we know what to do with coffee and cake. And when you're in a place like Jerusalem where there's plenty of good coffee and cake around, you think that stuff just grows on trees. But if you really think of the amount of work that goes into producing, like there's a field somewhere which you have to plow, irrigate, harvest, and so forth, the amount of work that goes even to defining in this stuff, let alone computing, I can't really do any sort of justice to so somehow, at the height of modern civilization, you think, well, that's just somehow stuff comes from free. But in fact, there's like for example, if you sow the seeds at the wrong time of year or move your recipe a little bit, you're not going to get a cake that people will enjoy. So okay, so this is to have something like this. It's important to have LCI. So it's important to have affine over reductive, to have a reasonable modular space like this. For this to have a good abstraction theory, you have to assume the pre-quotient is LCI. Like for example, if I take T star G mod B, it's unknown how to write it in this form in general. It's a kind of basic problem in algebraic geometry to either write T star G mod B in this form or show it cannot be written in this form. So for type A, you can do it since in the Kajima query right. In general, it's unknown. So so to have a good abstraction, the LCI hypothesis.
It is that you mean X, not stack. That you're talking about.
You want to embed it in the stack.
Yeah, you have to embed it in this kind of stack.
Just out of curiosity, for classical groups?
I think for classical groups you can do it. Yeah, I think. Yeah. So then. Somehow these issues are slightly disjoint from having a resolution. So and then so if in addition if in addition it's symplectic, that is of this kind of form, symplectic stack of this sort of form, then this moduli space. So if it's LCI, it has a certain virtual structure sheaf. Under the symplectic hypothesis, there's a certain self-duality to that structure sheaf, and you can define some symmetrized virtual structure sheaf. It's like the virtual A-roof genus of these moduli spaces. And so then you take this object, you multiply it. So this map has a certain degree, which is what's the degree of a map to the stack? It's just the degree of the associated. So first thing is you have a G bundle over a curve that has a certain degree. So that's the degree of the map. So you select degree. And right, once you fix the degree, then there's some properness about this map, so you can push forward. So maybe you can push forward under the map, not evaluate. You can push it forward. Maybe I took too many points here, so maybe let me have one. Oh, okay. So let's say I have 3 blue and 2 white points. So you can push it forward. Yeah, to have this, you really need a lot. Not just to have just virtual structure sheaf, you need LCI. To have a symmetrized version, you need some self-duality, which comes from the fact that this is symplectic stack.
But LCI is like existence of some kind of embedding.
Yeah, like I said, it's a basic problem in algebraic geometry which I know how to solve.
Right, but does it depend on this embedding?
No,
It does. Like for example, you can the Hilbert scheme of 2 points is abstractly isomorphic for T star P1 cross C2. Then so which means you write it as a quotient by either JL2 or JL1, and the answer will depend on. So
So it's not in the answer of the problem. It's, for instance, for T star G mod B. We really it's not. It wouldn't, even if we knew it is a GIT quotient. It won't be sufficient for.
so the answer for the problem we know the answer for T star G mod B. Yeah. So that's so then there's of course in this case it's an assignment to create a theory that reproduces this answer that particular answer. Right. So in some sense the problem to actually define the kind of theories that already Sasha discussed and I think Anton will discuss is somehow define what their basic computation in those theories. Yeah.
Correctly, Pasha's question.
Uh-huh.
To understand correctly, you have two players here. You have X, which is variety, and you have a stack.
Yeah.
And given an X, you're really not given a stack.
Right.
Stack can be different. So your computation
exactly depends on the stack. Yeah.
And not on your open.
Exactly. Yeah. So this is a computation in this. Yeah. The way this phrase this is a computation in certain three-dimensional gauge theory where the group gauge group is G and it acts on wherever that modular this moment map is defined, and this is where you do the computation.
But what do you use for this?
It uses more than
sorry.
Yeah.
It seems to me
Mm-hmm.
the stack is some completion of X.
Yes.
That you really you really need complete variety. As stack is some property of completion.
Yes, absolutely. Yeah.
No,
in other words, you can write this moduli space like you can write a part of this moduli space which just maps to X. This will not be proper, and you just to invent some quantification of that moduli space, okay. Which is in particular you can start with maps of degree 0. So.
Yeah. No, but it also uses representation of X as a quotient of LCI space, modular reductive group, which is not equal to G. It's a different group.
Yeah.
This I'm not sure. Maybe the only thing you need is a stack.
Yeah,
well, Andrei said it depends on this representation.
No, it doesn't.
Huh?
I mean, the moduli problem doesn't depend on the presentation of the quotient.
Yeah, that's what I say. This way the correct answer.
I mean, you need it to have some property for each. If I have two different X mod G and Y mod H, they can be the same stack.
Oh, the same stack, yes, of course. But if it's, I think the question, if it's just a question of the same X, then it depends. But the same stack, of course, the same stack, yeah, the same stack, yeah, yeah. So anyway, I'm going to push this forward. I'm going to take this sheaf and push it forward to. So this will be. Maybe I'll write push forward, and this will push it forward to where? So first I have my curve. So in fact it goes to it doesn't need to be stable. So it really goes to the moduli stack of some genus and some number of blue plus white points. In fact, maybe like this, because the blue points they cannot. These are the kind of weighted pointed curves where the blue points have to be disjoint, whereas the white points can light and heavy points, as people call them. And then cross some number of copies of X. In this case, it will be 3X, and some number of copies of the stack. In this case, it will be 2. Right?
So X comes from crosses.
X comes from at the blue points I have evaluation map to X. And I can also have other points at which I would just go to the stack.
Do you use crosses in the
No. Crosses are singularities. They're dynamic. Yeah.
And what does it mean to go to the stack? So what is the?
Just evaluation. There's the natural evaluation map
You
here.
require some points to be stable and some points to be.
Yeah. Right. Some points are required to be stable, and some points can go evaluate.
So 3 is B and 2 is double.
Exactly. Yeah. So it is in this, and this is in 3, and this is the. The heavy are the blue points. The heavy points go. They cannot collide, and then and they go to X. And so this satisfies all the usual. When people call it, I forgot how people call this stuff. Cohomological field theory. In that sense that it satisfies certain gluing axioms, and so this is This is some kind of, I mean, it's not cohomological because it's a K-theory class, but it's otherwise it's like this cohomological field theory. It satisfies, like if my curve degenerates, then the restriction to the locus of nodal curves is obtained by. I suppose you're familiar with this notion. It's like topological field theory, but yeah. Yeah. So that's the Hilbert space. So the Hilbert space is the K theory. Whatever that, there's also some action of the flavor symmetry group, maybe on X, on here, on everywhere. There is an action of what I think Sasha denoted GF, in flavor symmetry group, and we can right. I apologize. So on everything there is some action of what I think Sasha denoted GF, this flavor symmetry group. We'll just can take maximal torus in there, and so the equivalent K theory of X is the Hilbert space of that.
So, I mean, what happens to the evaluation maps to the stack?
Yeah, but it's quote. There's a map. There's some. So there's a K theory of abstractly. There's a map from K theory of this to this, and there's some kind of way how it really. I mean, doesn't really factor through this over, so to speak, over constant, but it factors over something depends on Z. There's some relations. I mean, in principle, you can stick in here, you can stick infinitely many things, but in fact, only finitely many will be linearly independent, and so many. So.
Does this space have a Hermitian form?
Well, this space has Hermitian form, yeah, obviously, yeah. Yeah. And so by general. By kind of right. One more thing is that this is I think this is roughly what Sasha meant when he talked about this kind of group object or algebra object over affine Grassmannian and this sort of thing. Is that if you have a group, then in fact you can define this object not. If you have this group, additional group GF, you can define this counts not for maps into the stack, but for sections of a twisted X bundle over your curve. So in other words, you can define if you have a group, you can imagine that. So by definition, again, a map to the stack is a section of some bundle, and the structure group of that bundle is the group G. But if you have an additional action of some group GF, you can also throw in a GF bundle there. So it's really this thing can be twisted by GF, which means you're gonna go to like some kind of moduli stack of maybe. So these are curve with a principal. GF bundle. Right, so this is, and again the kind of gluing is that you allow, as you break a curve, you allow this bundle to degenerate arbitrarily. I mean, for any degeneration of the bundle, you have the same gluing.
No, sorry, tell me about the notations. You have an arrow.
Yes. Yeah.
And the left, you have some kind of a sheet.
Yeah, well, I'm saying that this pushes forward the current K theory of that.
Okay, fine.
So, yeah, I apologize. In principle, you have this guy is defined in dB Koch, this object. You can push it forward to an object in dB Koch. In enumerative geometry, we don't like doing this. I mean, I don't like doing this because the basic thing in enumerative geometry goes back to the fathers of the subject is deformation invariance. You'd like to define something that you can deform, and of course this is somehow once you do this, then you go to K theory automatically. But in principle, you can study this as a sheaf, right? And so next step, this object satisfies. This is like some kind of decorated cohomological field theory, which is.
Since you're dealing with algebraic variety,
Uh-huh.
In principle, there are two ways to understand order K-theory. There's topological K-theory and algebraic K-theory.
Right.
Are you talking about topology?
I like algebraic K-theory. For this spaces, that's the same. Yeah. For this, so yeah. Yeah. So this is. So okay. So then, and like I said, this satisfies all the kind of gluic axiom with this. So if you take, so it means if you break a curve, you have to degenerate the bundle. You get to degenerate the bundle any way you like. So it still satisfies gluing. And so there's a general Giventhal Telemann philosophy that says this is determined by very, very few pieces of data. And so in principle, so the kind of, so maybe I'll erase this. So this is it. Everybody had enough. Everybody look.
Theory works usually in all cases, only in simple cases.
Yeah, right. But in most of the cases of interest, so like we really the thing we really care about geometrically, where X is like some Hilbert scheme. So the case where we really care was X is a Hilbert scheme of a surface, in which case this is Downson-Thomas theory. This object is the Downson-Thomas theory of a total space of a bundle over that curve. And in that case, it's semi-simple. That's the main case for us, but somehow, yeah. In general, one can. I know, but in all examples we understand, they're all semi-simple. So. It means the quantum ring semi-simple. So then, so maybe I'll write it. Dima knows. I mean, you know what I'm going to write. So this is. So the one piece, the main piece of data that goes in this kind of Telemann classification is just 3-pointed P1. This is just one curve and defines you a product. This is the main thing, and this product has to be semi-simple. Yeah, that's commutative. Exactly. Yeah. So this is. So, but then in the theory that I'd like to describe, there are more basic pieces than this because this I'm going to talk about the stack, so the stack of the curves, and then there are more basic pieces. And one such basic piece is okay. Well, maybe I have a dry, like the two kinds of points. I have the dry and the wet. So there is the first piece of the theory is this with two blue points. This is trivial in cohomology, so you haven't seen this before. But this is unstable. This has an automorphism, and I have to tell you what that space is as a representation of Q. Right? So this is in the subject. This is what we call the glue matrix. This is really defines you a quadratic form on my Hilbert space, and with this quadratic form, anytime you have to in the gluing we've been discussing, you have to use this quadratic form. And so in cohomology that stuff is trivial, but in K theory it is not, and there's several remarkable. So in general, so like I said, you can define it. You can there are various flavors of quantum K theory. You can define it in something like this in all of them. In general, it's something very, very complicated. But in our case, it will be something something beautiful. And so this guy, so the first property of that, the way I set it up, this will in fact does not. So this means rigid. This is some virtual representation of this automorphism, and in fact, it's trivial. So this is already this is from the point of view of in K theory. It's really interesting. And what this guy is in the language I'm going to describe. So what this is we'll get there. Remember, I had this picture. Maybe these were enigmatic pictures yesterday, but in the affine dynamical Weil group of a certain of a certain quantum loop algebra, there is the longest element in the finite. So if so, there's some affine hyperplane arrangement, but around the origin, if I look at the origin, then I have the longest element in the finite Weil group, and this is this glue matrix. And you see the fact that this independent of Q is that because Q was coming into the way the Q was coming into equations from the somehow if a hyperplane doesn't go through the origin, then it involves a certain power of Q. So the fact that this goes through the origin has to be rigid. And this is, I mean, if you think what does it take for this stuff to be rigid? Well, it basically takes everything. It has to be really the fact that this is symplectic is very much used in this.
So this is an operator on which space?
This is an element. This is an element of this glue matrix that sits in K theory of X T tensor square. It's abstractly formal power series in Z, but in fact, like we're discussing, somehow the basic magic that happens in the theory is that this in fact converges to a rational function of Z. So this is, to continue my discussion with cake and coffee, all the work in setting up this modular problem is just to get you started. Then you have to compute, then you have to countable many problems of growing complexity, you have to solve them all. And generally, so this, somehow, enumerative geometry is not a new subject, and that this is the subject that is somehow, generally speaking, people drawn to the subject like this kind of challenge. Means there's like very.
Where does that come from?
Oh, this is from degree.
Okay.
This comes from you sum up curves of all possible degrees. So
what is it when X is T star Q1?
You know what's the reflection in this in SL2 there's is UQ of SL2 there's this reflection. This is going to be it. Yeah.
But what is Z?
This dynamical variable. So the fact that this is, like I've said, the fact that this is countably many. Generally speaking, this is countably many problem of growing complexity. The fact that you can solve them with a rational function Z, it's a miracle. And you would think that this is that you specifically invented the kind of problems that you can solve. If it were not for the case that in the case when X is the Hilbert scheme of a surface, this has a direct interpretation in terms of this three-dimensional counts, as Davesh somehow advertised in his very first lecture. So this is anyway, somehow it's a good miracle.
Usually there are many dynamical variables, not one. And here it's only one. How come?
No, Z is an element. So Z is an element in this Picard torus. It's an element in Z, which is peak X odd times C star, which is also the Cartan torus of my group.
And it's supposed to also depend on Q?
No, that's a miracle. It doesn't depend on Q. Geometrically, it seems to be like no reason this doesn't depend on Q, but in fact it doesn't.
Dynamical reflection for classical algebra.
Yeah, this is the longest element in the finite Weil group. Yeah.
But for non-quantum group, for usual.
For quantum, so okay.
It's quantum, it has Q.
No. This is Q. That Q is H bar.
Okay.
Yeah. So this I emphasize variable Q has nothing to do with UQ.
Okay.
That variable is H bar.
Depends on H bar.
On H bar it depends. Yes, of course. So H bar is the way to the symplectic form. So the next piece of data is when you take. So this is one piece of data. The next piece of data is you have to have some kind of notion of three-pointed invariant. But if you'd like to do it equivalently, you think, well, how can I have three-pointed invariant equivalently? Well, the way to solution to that is that you can have, so you have a blue point, another blue point, you have this Q action, and then you can put another white point on top of this blue point. the way that moduli points are set up, this is not a stupid operation. And so at this original white point, I can take a pullback of a line bundle for my variety X. This is, like I said, it's not a stupid operation. It's not gonna be. It's not like you.
So if your line bundle is trivial, you'll come back to.
Yeah. There's somehow nothing's going on. Yeah. So this is again some kind of quadratic form. But now, if I multiply it with this glue matrix inverse, now I'm going to get an operator. So, like I said, if you
say I put a line bundle, this means that you're really it's the like this flavor group, or what does it mean?
No. So this is the way it's technically done. What does it mean to put some insertion at a point, at the white point? You take the preimage of so the actual quasi-map goes through some kind of destabilization. You take the preimage of this white point. You take cohomology of the tautological bundle on that preimage, and you take the determinant of that. And this is what it means. This is everything is flavor group equivariant, but it's a line bundle right now. So this is the operator. This is the operator of the quantum difference equation. Even line bundle is just a character of your group G. What?
This is the operator of the quantum just.
Of the quantum Q difference equation, right? So remember, in Davesh-Stock, there's the quantum differential equation the quantum differential equation was d by d lambda, some function psi was lambda times psi, where this is where this is this operator lambda star means I took an extra point and I put at this extra point I put C1 of, so to speak, I put that, maybe I'll write I'll write lambda. So lambda is now an element in H2. And the point about this equation is that if you want to somehow cohomologically correct version, the cohomologically correct version is to put here epsilon, where epsilon is an element in the Lie algebra of C star Q. Right? So there is this two-pointed curve has automorphisms, and epsilon is really the weight. Out of differential equation, you can scale out this variable. It's not a very important variable in the differential equation. But in the difference equation, this is an important variable. And the point in the differential equation, this side does not depend on epsilon. Right? So you can put that, you can take this white point away from the blue point, and you can have this. But in the difference equation, in general, the right-hand side of the difference equation does depend on the shift variable Q. And so this is to have that, you have to use this sort of construction. Okay. And so what this guy is, in terms of the same picture, this is, remember when we had this affine arrangement yesterday, and I'll remind you what the setup. Oh, okay, this is my best. And lambda. So lambda is an element in peak X. And peak X was acting by automorphisms of this picture. So there was some translation. There was some translation by lambda, which was automorphism of that picture. And the translations by lambda gave us commuting difference equation. And a theorem, which is, like I said, it's easy to state, but not so easy to prove, is that I apologize, really isn't. So that in fact this quantum difference equation is the action. So this difference equation, which you define geometrically, is given by the corresponding element in. So that's the same. In other words, you have a map from peak to your dynamical quantum dynamical. Dynamical Weil group of a certain U H bar G hat And this is a lattice in here, and this operator is that. Right? And then the third piece of, yeah.
Can you explain what the Q is? Is it an action on the domain curve as well?
Yeah, it's action on domain curve. Just acts on domain curve.
So this is like an additional thing in this quasi-map story that you actually have?
Everything is defined equivalently with respect to both the automorphism of the source curve and the automorphism of the target. So any computation is a representation of these groups. So this
Just that it's a parameterized curve in this case.
yeah. Yeah, all curves are parameterized. I mean, we don't mod out by automorphisms. We keep the action of automorphism.
And so in higher genus,
It's the same.
you just get some kind of very degenerate thing which has, I mean, if you took a irreducible, a smooth curve genus G, there's an automorphism like this.
Well, I'm saying what I'm saying is that this by this kind of Telemann philosophy, the whole thing in all genera is determined by very few pieces, and I'm telling you the basic pieces. I mean, I'm telling you the pieces more basic than this, because in all cases we know this guy. In all cases we know this operators generate the corresponding operator generate the quantum ring. So this will be a more basic thing. This is genus 0. This is the genus just here with 2 mark points. Yeah.
I mean, if you have some action on the domain curve, you don't want this thing to sort of like be consistent through.
Oh yeah, everything is like I said. Everything lives over. I mean, you have some vector space for every such count is some vector space in which the automorphism of both the source and the target act. So I don't know. Is that
the question probably is that when you refer to Telemann and given that there's a statement that everything is high genera is reduced.
Yeah.
But here you kind of axiomatize it as an input data.
No, I don't axiomatize. I'm just explaining. Then in this big count theory, you can study these pieces anyway. It's interesting to study these pieces in any case. I'm just saying in some favorable circumstances they determine everything. But this is interesting. This is interesting to study in any event.
So you basically don't care about high genera.
Maybe a polite way to say it is people have to. No, I do. If you study like threefolds, so if you study threefolds fibered in surfaces over curves, that defines you some kind of stuff. But if you, I don't know. But since
It has to do with the fact you only deal with H2.
No. Yeah, anyway, somehow. So this is okay. So then the third piece of data, crucial piece of data again, is that I now take again 2-pointed curve, but now I take a non-trivial GF bundle. So I have some element, some twist by some co-character. Maybe I'll write it A sigma. This is a co-character. A sigma is a character in that, right? It's a line bundle. No, it's not a vector. It's a principal bundle, but so it's a principal. Yeah. So this is in this flavor symmetry group. And so then. So again, this is a quadratic form. To make it an operator, I multiply by G inverse. And this is this equivalent. This is this shift operator. This is Davesh already appeared in Davesh's talk.
Take a guess at that. So you're actually looking at maps to X cross P1 or something like that?
No, you look at so again, a quasi-map is a section of some bundle. That bundle, if you have an outer automorphism, you can further twist by some outer automorphism.
Take like a twisted X
Yeah.
over P1.
Yeah. I mean, it starts as a twisted, some kind of bundle, and then you further twist it. Right? And so what this guy is the corresponding. So this is the exact same thing now sigma. So now in my so this was a picture in Lie algebra of my Kähler torus Z. And then there was a picture, kind of a mirror dual picture. We'll draw in a mirror dual in some kind of dual way. I mean, it's a different. It's not. It's a different. In general, so we're used in usual Lie theory. You have like roots and co-roots. These are like roots and co-roots. And in usual Lie theory, you have roots and co-roots. They're basically the same. You have to spend a lot of time in Lie theory class to appreciate the difference between roots and co-roots. But here they're visibly different. They live in spaces of different dimension, and just somehow very different. And so then there's this Lie algebra of A, which is maybe I'll inside of this I take a torus that preserves symplectic form. And so then similarly here I have this translation by sigma. And that's that operator. I haven't defined what this guy is yet, but I'll do that. This is the next step. All right? So everything is so this is. So
Okay, first will be just special case on second thing. So that's right.
No. This is
first producer.
it's right. Yes, exactly. Yeah. So if you know the second thing, then you know the first. Yeah. Yeah.
Now, if somebody gives you the present, so first, second, and third.
Yeah.
Could you tell when it creates a good field?
So maybe let's go back to T star G mod B. For T star G mod B, all this theory is supposed to be this Cherednik's double affine Hickey algebra story. Yeah. And the question is there a reasonable geometric background for this? Yeah, so I don't know.
Teleman's argument in the semi-simple case.
Yeah, it will produce you something, right? But then
I think it's more.
Answer David's question.
no, but then you'd like probably some enumerative theory to go with it, to come with some from some enumerative theory.
I think more.
Yeah.
The way which can be completely relevant. I think about biological field theory,
Mm-hmm.
which says that if you give something which corresponds to a point
Mm-hmm.
in some kind of condition,
Yeah.
some condition, then it produces automatically the theory.
Yes.
So in a sense, roughly speaking, very simple piece, very complicated description, very simple piece of point, gives you everything.
Yeah.
So my question is, whether behind what you are saying is a similar turbulence that it's kind of you can start asking.
Right. So yeah, like maybe. So I have some thoughts about what you said, but maybe they don't belong here. So maybe we can come back to that later. And so right. So now this is like I said. This is some kind of yeah. This is anyway. These are and right. Maybe before I erase. Of course, since everybody in this conference is supposed to discuss symplectic duality, of course, symplectic duality permutes these two objects. So, all right. So then, all right. So now I have to tell you what this. Have to somehow begin to tell you what the corresponding. What's this object? So we know. What is this object? Starting with what is this object? Starting with what is this object? And so there's some layers. So, Nakajima quiver, right? And so there's some quiver Q. And so as Davesh explained, associated to Q, there is certain Lie algebra, GQ. It has a very interesting structure. People like Ben, for example, here, he did very important work on the structure of Lie algebras like this. Very interesting Lie algebra. Then the way Davesh and I construct it is through matrix elements of some classical R matrix. We first construct the classical R matrix, and then we reconstruct the Lie algebra from it. So classical R matrix means solution of the classical Young-Box equation. And so similarly, this whole loop group, quantum loop group, this is constructed from, is in the way that Davesh explained. This comes from matrix elements of certain R matrix. Maybe this is a pedestrian point of view. Maybe a higher point of view is you make K-theories of Nakajima varieties into a braided tensor category, and then you realize then it's your choice how to present that category as a category of representation of some yeah.
It means constructing some kind of fiber function.
Well, the fiber function is just yeah. What you need is the tensor structure on that fiber function. Yeah, that's right. Yeah, exactly. Yeah. So then
it's not. It's like meromorphic braided category, right? It has poles. Braiding has poles, and it's squares to the identity.
Yeah, right. But anyway, you can. This is somehow. There should be a chapter in your book about somehow reconstructing. So there probably is a way to reconstruct without taking matrix elements. But if you take matrix elements, that works just fine. Yeah. And so what is this? Where is that R matrix comes? Where is that R matrix sits in the pictures we discussed? So we remember we had the picture. So there was this Lie algebra of the torus Z, and that has So Z was, so this is just pickaxe. In this case, maybe I'll draw it tensor R. So, and here you have this alcoves. And there was another picture. So maybe this was not the very best use of my Blackboard, but so maybe I'll. For now, I only want to sit near the origin. So this is a picture in the Lie algebra of Z, and this is a picture in Lie of my torus A. So now what will happen is that here I have to fix an alcove. Fixing an alcove here, this is called the, so choose, so it means a choice. Choose slope. I'll explain in a second what this means. And once you made this choice, then for every cone here, you should think of this. So okay, the way to think of this is that this is a base of a certain. So this is the base of like a covariant cohomology or of a covariant K-theory or for whatever in something, and the fiber over every point is the fixed locus of the corresponding. So if I have little a, that what sits over A is the fixed locus of A. So in particular, over 0 sits X itself. And so then, and if you have and this form, you know, some kind of sheaf in the sense that corresponding to a cone, like if you have a cone adjacent to a certain a face of a certain dimension, and you have a map. So here a map will be from equivariant K-theory of the fixed locus. Well, if A is generic inside a cone, that's the fixed locus of the whole thing. And then this goes to the K-theory of this. This is the general shape of this map that Davesh described. But in K-theory, it gets an extra variable, it gets an extra parameter corresponding to the slope. And how does explain this parameter in terms that will make sense to Lie theorists is that algebras, so it has a certain geometric meaning. Maybe in the next lecture I'll try to explain what this is. But why there should be an extra choice is because this object, sorry, maybe not, this object here is a Hopf algebra in many different ways. In many different ways. Right? We usually so in somehow the usual experience with loop groups of n-dimensional Lie algebras, they're all kind of the same except the one at infinity, which people call the Drinfeld coproduct. But for this kind of stuff, so you know, there really are different coproducts, and algebraically or geometrically they correspond to alcoves in this picture. So if you want to construct R matrix, you need to make this choice here.
No, but even in the usual case, you have a Lucid braid group action, which does not preserve the coproduct.
Yes.
So it maps a coproduct to a new coproduct.
Yeah.
Exactly, yeah.
And those corresponds to the alcoves.
Yeah, but then all the alcoves are somehow in some sense the same.
Yeah, because
But
they're related by group action. But
yeah.
if you are saying that in general, they are not even related by
Exactly. Yeah, in general we're doing Lie theory without groups, and so this is really, and the geometric meaning of that I'll try to explain next time.
But
and
all
so
these coproducts are related by twists. Yes, is this right? Or
well, I don't know how to say. I mean, this is you.
they define the same tensor category.
Yes, right, but it's so I don't know. So we'll get there. And so okay. So then you get this map that depends. So in other words, you have this stable. So you have to choose. So the data is you have to choose a slope here, which may be slope S, and you have to choose a cone here, which is maybe a cone C. So there's some kind of cone and slope. You have a map from K-theory of the fixed locus to the K-theory of the ambient space. And R matrices have to do with changing the cone. But this is what's explained in Davesh's talk. But you can consider like a lesser transformation, namely you can ask for what's going to happen with this transformation if instead of changing the cone I change the slope. And so then if I change the slope, so if I go to a different adjacent alcove, so then the change in the slope is recorded. So change the slope, change S. We get something which is we call the wall R matrix, R wall. This is the wall R matrix. And the correctly normalized, it depends on very few variables, because it's a very small change if you normalize it correctly. It satisfies Young-Baxter equation, but opposed to this depends on all the covariant variables in the picture, whereas this depends on very few. And and so then this is so This is defined. So this is corresponding to this wall R matrix. I have a map. So if I now apply, so maybe I'll say it like this: the R matrix. You can write like this. So the R matrix, if you're trying to write the R matrix, so maybe I'll write. There's. Yeah, right. So maybe I'll write. There's this kind of Hiroshkin Tolstoy type factorization. What it says the following is that if I want to fix, that says that if I want to go from, if I want the R matrix that goes at a fixed slope from some cone to some other cone, then this I can factor. Maybe this is. This is very basic. So this is the construction of this map is complicated, but its properties are very simple. And this gives the following thing. It tells you if I want to, at a fixed slope, I want to go from a cone to some different cone. And I might as well do it like this. This can be given by infinite product. If I go from
this R is step S times step.
That's right. This means when I right exactly. So this is what I mean is that you go. Yeah, exactly. So this means so this is my it's my alcove, and then I can choose a path to infinity.
And in the A, you only consider chambers, not alcoves. Yeah.
Yes. Yeah. So right, we will. There's an alcoves picture, but we'll get to there maybe. It will come later. So then, so this you can write like this. You can write as in the middle they'll be going through at the slope kind of infinity from this to this.
Which infinity?
Well, it's like at infinity this at this infinite slope.
No, is it important?
So you're right. It's important which infinity. Yeah. Yeah. And then here there'll be an infinite product of fixed wall R matrices. So you take at the fixed you take kind of from the slope to kind of the next slope at a fixed. Maybe I guess it's prime.
So stable envelope is one of these products, right? Is it true that step CS equals to one of these products? Or
No, this is step is some. I mean, step is a map from one space to another, where this all map to space to itself. Yeah. In other words, if you want to change the slope, it's better to change it at infinity. If you want to change the cone, it's better to change it at infinity.
It's simpler.
Simpler, yeah. So this is like the Drinfeld, some kind of Drinfeld R matrix, and this is this. But
this step is obtained by Gauss decomposition.
Yeah, exactly, yeah.
And this product is obtained by kind of Birkhoff decomposition.
That's right. So, so this tells you the important thing is since the algebras are constructed extracting matrix elements, that tells you that there's an embedding of UH bar of just this G wall. This is not an affine. This algebra, this R matrix, does not really have a spectral parameter, because the spectral parameter dependence in this matrix is stupid. You can turn it away because the way it's defined. Yeah.
In Dava there was a co-root of the torus A.
Yeah.
And here there's both alcove and a cone. And how do those two co-roots of A?
Yeah. These are.
How do they correspond?
So the C is the
This is like, yeah, these are like equivariant. These are equivariant roots, and these are Kähler roots. And in general, they have nothing to do with each other, but there's some compatibility. They have a different set of roots that's somehow set. So what I'm trying to say is that this wall arithmetics. This does not have no special parameter. Really. And so this, since the taking matrix element of this product involves taking matrix, this means that there's an embedding of this guy into my here. And so this object is a rank 1 quantum group. And in a rank quantum group, you can write by universal formulas, which, since the formulas are universal, in particular, they apply for SL2. And since they apply for SL2, you can find them in Pasha's paper. So just from the tensors of a Hopf algebra, you can write some universal expression of some reflection of the variable z, where z is in Cartan of this. So this is a rank 1 quantum group. In Cartan of that is 1 C star, some universal expression you can write in terms of tensors, in terms of canonical tensors, which is like analog of this Casimir expression.
But you also, sometimes it is also Heisenberg, yes? This rank 1 thing.
Sometimes it's some, most of the time, it's some hyperbolic beast of which we have really little control. This is for general Nakajima variety. Right, so most of these roots are hyperbolic.
Okay.
Yeah, so most of the roots are just really bad.
So you can only find in the case of real in my paper.
No, but you see, I said there's a universal formula in canonical tensors of a Hopf algebra. So in particular, since the canonical tensor, they know nothing about. In canonical tensors, what is it? There's the R matrix. Then from the R matrix you write fusion. Then the fusion you do some kind of antipotent multiplication, and you get this answer, right? So this object knows nothing about whether you wrote your real or imaginary or something, right? So this formula is universally true. So in particular, you can find it in your paper.
But this explanation is in your paper with Smirnov.
Yeah. So this construction, yeah. So there's some universal object here, and this guy. So this is a function of one variable, but of course there's this z is really. I mean, this my big torus z. There's a map here, right? So this is why this if I reflect through a particular wall, this only depended on the equation of the wall. And so this guy is generate. So these are the generate.
And then the coefficient of quantum difference equation is obtained as a product.
Exactly, yeah.
This for passing from Okounkov to the shifted wall.
Exactly, yeah.
So you cross a certain number of walls, and you have to write.
Exactly. What Pasha says is a theorem. It's kind of, I mean, it's not an easy theorem to prove, but it is a true theorem. So this generalizes the formula. So again, this is at the dawn of the subject. I'm over time. But.
Can you say which Pasha's paper is it?
Pasha has many papers, but the one I particularly like, it's called
Dynamical Y groups.
in applications. Applications. This is Pasha and Varchenko. Yeah.
Without Varchenko.
With Varchenko. With Varchenko.
Okay, maybe we should finish now and have some 5 minutes for questions. Does that sound
Yeah, sure. Yeah, but
no, and then some 10 minutes.
but maybe I'll just make it clear that this is a theorem, that this quantum difference equation they're really given by the lattice in this group, and the theorem was envisioned by Pasha because somehow this is the correct. He explained to everybody. He knew that this difference connection is the correct generalization of a Casimir connection. So the theorem that Davesh described is that in Valerius language, that this is the quantum differential equation is Casimir connection for a certain Lie algebra, and Pasha knew, maybe he didn't, even though he was afraid of imaginary and hyperbolic roots, but he knew that the some kind of this kind of dynamical connection is a correct generalization of the quantum connection.
And this RS from C to C prime is monodromy of this difference equation, right?
No, the monodromy of the difference equation is elliptic stuff.
Okay, guys.
Of the differential equation. So the monodromy of the differential equation you get from sending this guy from degenerating this.
I think so many questions.
Yeah.
So let's send this paper.
Okay.